When you step onto a bathroom scale, you're usually just looking for a simple number to tell you how heavy you are. But that number isn't a permanent feature of your body. It is actually a real-time measurement of an invisible pull between you and the entire mass of the Earth. Which raises a strange question. If everything with mass pulls on everything else with mass, why aren't the chairs and desks in this room sliding across the floor toward each other? The answer lies in Newton's law of universal gravitation. This formula shows that the attraction between any two things relies on two exact variables, the mass of the objects and the distance between them. By understanding how those two variables interact, we can explain why our feet stay firmly planted on the ground and exactly how we can weigh the stars. First, let's look at mass. The force of gravity is directly proportional to the amount of matter involved. If you double the mass of an object, the gravitational force doubles right along with it. Distance, however, works differently. Gravity is inversely proportional to the square of the distance between the object's centers. Because that distance is squared, moving objects apart causes the attraction to weaken drastically. Doubling the space between two objects doesn't cut the force in half, it drops it to exactly 1/4 of its original strength. We can apply this exact math to our everyday lives. When you stand on the ground, your weight is simply the gravitational force between you and the Earth. By taking that universal formula and stripping away your personal mass entirely, we find the acceleration of gravity on Earth's surface. The rate at which you fall has absolutely nothing to do with how heavy you are. It relies entirely on the massive size of the Earth and exactly how far you are from its core. Most physics classes treat that acceleration as a strict constant, assuming gravity pulls the exact same way everywhere on the planet. But the Earth is not a perfect sphere. Because it spins, it bulges slightly around the middle, making it wider at the equator than it is from pole to pole. Since the surface of the equator is physically further from the Earth's core, the gravitational pull there is weaker. If you step on a scale in Ecuador, you will weigh slightly less than you would standing at the North Pole. If you start climbing, that distance increases even more. The higher you fly into the sky, the weaker the Earth's gravitational grip becomes. So what happens if we reverse course and dig deep into the Earth's crust? If moving closer to the center increases gravity, you might expect the pressure to keep rising forever, but it doesn't. As you descend, the mass of the rock above you begins to pull upward, canceling out the pull of the rock below. By the time you reach the exact center of the Earth, gravity drops completely to zero. Your perceived weight is never a fixed number. It is a hyperlocal, dynamic condition dictated entirely by your exact physical distance from the center of the planet. Once we zoom out past the atmosphere, we face a new problem. If the Earth's gravity is constantly pulling inward, why doesn't everything in space eventually crash back down to the surface? When scientists launched the first artificial satellites, they proved that an object could remain perfectly suspended in a continuous orbit. The Moon is locked in this exact same gravitational dance, following a massive circular path around our planet without ever falling out of the sky. This circular motion requires a centripetal force, an inward pull that keeps an object moving in a curve. In space, gravity provides that inward pull. An orbit is essentially a balancing act. These objects are constantly falling toward the Earth, but they are moving sideways so fast that as gravity pulls them down, they continuously match the curvature of the planet. They are permanently falling and permanently missing the ground. By recognizing that gravity is the centripetal force, physicists can set the two mathematical formulas equal to each other, creating a completely new tool. When we factor in the time it takes an object to complete one full orbit, called the orbital period, the math simplifies, the variables cancel out, and the equation transforms into a direct formula to calculate mass. This gives scientists a remarkable ability. They can determine the mass of any massive celestial body simply by timing how long it takes another object to circle around it. By carefully observing the Earth's orbital path and speed, astronomers gathered all the variables they needed to calculate the exact mass of our central star. The universe operates on a single, elegant law of scale. The exact same mathematical rule that pulls a falling apple to the grass is what keeps the planets turning and allows human beings to weigh the cosmos.